Hello, everyone. Good morning. Welcome to PyData Seattle. This presentation is called Quantifying Uncertainty in Time Series Forecasting with Conformal Prediction. We are in the St. Helens room. Our speakers today are Fede and Max. They are both co-founders of Nixla. And we will, in this presentation, we'll be exploring the use of conformal prediction in the context of time series analysis. So please welcome Fede and Max.
Hello, can you hear me? It's the mic, okay, great. So I'm Max, I'm co-founder of Nixla. This is Fede. Fede uses the non-binary pronouns they, them, and I use the binary pronouns he, him. Today we're going to be speaking about conformal prediction for time series, and the outline of the talk is as follows. We will begin by stressing the importance or motivating the importance for time series analysis and time series forecasting. Then we're going to show you how to perform scalable time series forecasting pipelines with machine learning methods. And at the end of the talk, we're going to address the problem of quantifying uncertainty. Let's start with the hype and with the hot topic that everyone is speaking about. As you're very well aware, ChatGPT 4 has a new API, and that was amazing. Also, Midjourney has released some incredible technology to treat images and videos. And in generally speaking, it seems that this new wave of large transformer models are making great breakthroughs in text, language, videos, and image. But what about temporal tabular data? What about time series? And in this particular case, it's not clear how a big foundational model would look like. And that's precisely one of the things that we are researching at Nixla. We believe that time, language, and perception are the necessary conditions for experience. They are the necessary conditions for intelligence, generally speaking. The temporal dimension is essential to understand anything that has to do with change, with growth, with decay, and we're trying to build those foundational models for time series. And we think this is particularly interesting and relevant because first-class citizens of the world, like businesses, institutions, and even systems, they don't speak in language, in images or language. They speak data, and they speak normally time series. We're trying to create that technology to understand, classify, and predict time series. So for 1 second, close your eyes and open them. And thanks to the magic of PyData Seattle, now you are the Minister of Tourism in Australia. And you get a lot of questions asked, but one of the most important one is how many tourists are going to be visiting the country next month, next year. And this is important because your colleagues at the transportation office ask you, how should I staff the airports? How many people should I put at the security lines? How many people should be in the control towers? But also your colleagues at the other departments of state, they ask you, how will the economy grow related to the inflows of different tourists in the country? And this is a classical example of an important time series problem. Here in the screen, you can see some graphs. On the y-axis, you have the number of tourists that are visiting particular regions of Australia. And in the x-axis, you have the time, the last 15 years. So you have the different values for tourism inflows in Australia for different regions. And what you're trying to do is, based on the past and based on certain exogenous variables like weather or special events or economic relations of New Zealand, which might be a competitor in the tourism inflows, you're trying to predict the future. The good thing is that you can't use machine learning methods to forecast thousands and even millions of time series. And today, we're going to show you how you can do that easily with a library, an open source library that we created called MLForecast. MLForecast is part of the time series ecosystem that we are building. Everything that we built is licensed under the MIT license, so it's completely free to use. You can do and build whatever you want. You can build commercial products if you want. That's fine. We have been trying to address the whole landscape of time series, not only machine learning, but also statistical methods, and also newer neural forecasting methods that are trying to solve the question that I posed at the beginning regarding foundational models in the field. So how does ML forecast work? We built this library trying to create a simple, scalable, fast interface for you practitioners to interact with it. And in reality, the only thing that you have to do to start building, we're going to start with a linear regression as a baseline, is to import the ML forecast class from the ML forecast package. You have to import, in this case, linear regression from scikit-learn. We support a natively interface with all models of scikit-learn, so you can import whatever model you want. In this case, we're using a classical model for time series called linear regression, but you could use nearest neighbors or support vector machines or MLPs or whatever. Then the ML forecast class takes a list of models. In this case, we're using the linear regression. You specify the frequency of the data. In this case, we have monthly visitors in Australia. And then you can specify date features like year, month, that might be important for the models to understand. Then you call the classical scikit-learn API interface with the fit and predict methods. You just pass the data frame. This data frame magically can be a pandas data frame, but it could also be a Spark data frame. It could also be a Dask data frame. Thanks to the partnership that we created with the folks at Fuke, we support basically any data frame, which is very exciting once you start having very large scale data. The columns that you need, the minimal columns that you need are the ID that specify the different, the unique ID of the data, the date column or the time column as we call it, and the target variable that you are trying to forecast. We also support exogenous variables, and the only thing that you have to do if you want to predict the next 12 months, that is the next year, you just call the .predict method of the ML forecast class. But ML forecast is also very powerful. We established a pipeline on how to create a linear regression, but we might want to do and include other powerful methods like XGBoost or LightGBM. So that sounds hard and maybe it would take us a lot of code. But thanks to the interface that we created, you just have to import those models, make them part of the list, and with those, I think, 20 characters, now your pipeline supports not only one, but 3 or n different models that you can compare against. ML forecast is also very flexible. If you have worked in machine learning, and in particular with time series data, you know that feature engineering, feature creation, lax transformations are, excuse my French, but they are a pain in the ass normally. And we try to simplify that by making them available inside the main ML forecast class. So for example, let's assume you want to do some target transforms because you want to scale the data, or you want to take out the difference every 12 steps to take out the yearly seasonality and have the models render better performance. The only thing that you have to do is import those target transforms. And inside the ML forecast, you can pass that as an argument. In this case, we're going to take the 12-step difference, and we're going to do a min-max scaler so the model performs better. So in just 3 lines of code inside the same pipeline that supports all the different models that I showed you, now we're starting to do interesting feature engineering. What about lags? If we wanted to include lags like the last 24 lags, that is the model for the model to learn the last 2 years, the only thing that we have to do is pass the lags argument, and we can start doing transformations on those lags. So in this case, we're doing the expanding mean for the last month, and the rolling mean and the expanding mean for the last year and for the last 2 years, which is the 12th and the 24th observation. So again, in a couple of lines inside the same class, you can have very scalable, robust, and simple pipelines. ML forecast was built from the beginning with scalability and speed on mind. All the optimization functions that we used are optimized using Numba, a just-in-time compiler, which makes it very, very fast. And it's also optimized for parallelism. The training and the prediction of the models support parallelization not only inside a single node, but thanks to our native interfaces to Spark, Dask, and Ray. Jules, thank you for being here. We support high-scale computation, which is amazing because now you are not horizontally bounded by speed or by storage. You can horizontally distribute your workloads using wonderful technologies like Ray. ML forecast is also tested. One of the things that we like to do is benchmark the things that we published. And there is this very famous data set called the M5. It's Walmart data for different years and different products. And we recreated in a Kaggle notebook that you can reproduce by yourself and used ML forecast to achieve 1%, or rank in the 1% percentile, so one of the top submissions, in under 3 minutes using the 4 CPUs that Kaggle supports natively. So it's very fast, it's very efficient, it's very powerful. We have also tested against other solutions like AWS Forecast. We're 24% more accurate than them in this same data set and 400% faster. We have also tested against Prophet, and we are far better. So back to our problem. We started with this time series and we wanted to predict the future. Now we used ML forecast. It took us a couple of lines. It ran very fast, and we're doing a wonderful job as ministers of tourism. So it seems that we are very happy and can keep working on our political campaign. But we start getting asked more questions. So not only how many tourists are going to be visiting Australia, but how many are going to be visiting in the best case, worst case scenario. At the end of the day, what's the range of possible visitors in the future? And this is important not only for people working in Australia doing tourism, but generally speaking for retail, or generally speaking for everyone that is doing optimization, inventory, or staff. So imagine that you are running an airport, and if you have more people than you need, then you simply have a little bit of cost for those extra salaries or wages. If you have less people that you need and more tourists come than you expected, then the lines start getting saturated, you lose your flight, and it becomes a whole chaos. So it's a lot better to be a little bit above than a little bit below the forecast. And that's what we call different quantiles. But also in retail, if you have a little bit more of inventory, then it's fine. You simply store it or pay the extra production cost. If you have less inventory to satisfy the potential demand, then you're losing a lot of money in lost opportunity sales. So it seems that we really need to have distributions. Another question could be, have there been any unexpected behaviors? Maybe some event that had some important consequences on the inflows of tourism. And that's what we call anomaly detection. And a very simple way of defining an anomaly is every value that lies above or beyond a certain threshold of the distribution that you are forecasting. And this is important. And yesterday, the people at Lyft gave a talk on how to do anomaly detection using Stats Forecast, another library of Nixla, to do almost real-time anomaly detection. The problem is that we just have point forecasts. What I showed you with the ML forecast is just a single point. We don't have any distributions. And we need prediction intervals if we want to start optimizing and answering the 3 questions that I just showed you. So it seems that things are not that fine. Hopefully, Fede can now help us solve that problem. He promised that he will help us define those intervals for the forecast, and I hope he does. They does.
Thank you very much, Max. So far, we've created a lot of forecasts for different time series, and then we want to quantify the uncertainty of those forecasts. So, what are prediction intervals? So basically, a prediction interval gives you an interval within which we expect the 3 values to lie with a certain probability. So for example, if we want to produce a 95% prediction interval, we want that the 3 values will lie in that interval 95% of the time. And this concept, it is a really key concept. It is called calibration. So basically, we are measuring the probability of the correctness of our model. So we have a problem. And the problem is that machine learning methods can't create prediction intervals natively. We need to produce a technique to calculate those intervals. An initial approach could be just to use the multi-quantile loss, and the multi-quantile loss allows you not just to estimate the mean of the forecast, but also quantiles of the forecast. And if you include that loss in your model, you will be creating a lot of quantiles, not just one. What is the problem with the multi-quantile loss approach? In general, it produces uncalibrated forecast. Here in the example, we want to produce a 50% probability prediction interval, and then we are calculating the 75 and the 25 quantiles, and we can see that the quantiles are crossing, so the forecasts are not calibrated. An alternative approach would be just to use statistical methods. The main problem with those methods is that they also produce uncalibrated intervals. So for example, here we are seeing a time series which exhibits a clear seasonal pattern each 24 hours. And the first thing we notice is that the mean or point forecast is just a straight line. And also, we can see that the prediction intervals becomes wider as long as the horizon increases. So if we know that there is a clear seasonal pattern, our forecasts are not capturing that. So this is a problem. Another problem with the statistical methods is that they assume normality. So in order for us to calculate the prediction intervals, we need to know the two parameters of that distribution, the mean and the variance. And once we have that, we can use that formula to calculate the prediction intervals. So it is a really hard problem because with the traditional approaches, we are calculating the mean parameter of the random variable, but we also need to calculate the variance. And it is really interesting because because we want to, or we need to estimate that pair of parameters for all the horizon. So for example, if we want to predict 12 steps ahead, we need to calculate 12 pairs of parameters, not just one. What is the solution? The solution is conformal prediction. So basically, conformal prediction allows you to use any kind of point forecaster and use it to calculate prediction intervals. One of the main characteristics of this approach is that it theoretically guarantee that the prediction intervals are well calibrated. Also, you don't have to assume any kind of distribution. So for example, in the statistical methods, we are assuming normality, but in this case, we are not assuming anything. Another interesting thing about this approach is that we don't have to assume any prior probability, for example, in contrast with Bayesian approaches. So basically, with conformal prediction, we want to construct an interval which is well calibrated by definition. How can we do that using time series? The main idea behind conformal prediction is that we can estimate the distribution of the errors of our model, and once we have that distribution, we can calculate the quantiles associated to the distribution, and after that, add those quantiles to the mean estimate, and after that, we will have the prediction intervals. So how can we estimate that distribution of errors? To do that, we can use cross-validation for time series forecasting. So basically, we can split the data in different windows, considering the temporal index of our data. And then we can forecast different values for different windows in our time series. And then once we have the forecast and the actual values, we can compute the errors, and those errors will give us the distribution or the expected distribution of the errors. How can we implement conformal prediction for time series forecasting? Fortunately, ML Forecast includes this feature natively. So you just have to include one additional argument to the fit method, the prediction intervals argument, and it receives a prediction intervals class, which receives two main arguments: the number of cross-validation windows we want to use to calculate the errors. In this case, we are using only for Windows. And also, it receives the forecasting horizon. In this case, we want to predict the next 12 months, so the forecasting horizon is 12. So after the fit method, we just have to call the predict method, and we need to define the level of our prediction intervals. In this case, we are generating two prediction intervals, one of 80% and the other one with 90%. So after that, with just a couple of lines of code, we have included prediction intervals to our forecast. And as you can see, some series exhibit a clear seasonal pattern, and the model, the prediction intervals associated to those series are narrower. And when the series is sparse or exhibits more randomness, the prediction intervals becomes wider. So that's it. In a couple of lines of code, we were able to create calibrated forecast for thousands of time series using machine learning. Thank you.
You moderate or we moderate?
Either way.
Please.
Okay, so I love that you included the list of models as an option for the input to your ML forecast. Does that mean that there's ensemble capabilities, or is it strictly comparing the outputs of each of these models? And if so, how are you comparing the outputs to determine goodness of fit?
One of the paradigms that we have in the whole Nixlaverse, ML forecast, stat forecast, and neural forecast, is once you specify the list of models, the output is a data frame that contains in each column the results of the models, and if you have prediction intervals, the model and the prediction interval. So creating ensembles is really easy. The only thing that you have to do is, for example, sum the column light GPM and XGBoost and divide it by 2, and you would have a mean ensemble in one line. So we give you all the different forecasts for all the different models, so you can either compare them or ensemble them or do specific choices. So that's up to you or up to the practitioner to define.
I've done a lot of time series work.
So one question. Can you hear it back there, or should we pass like a microphone?
Yeah, sorry. No worries. I've done a lot of time series work using like the Profit library, but mostly like the Darts time series library. And there's a lot of, I think, overlap between what you guys are doing and what they're doing. And I guess you mentioned that there's a performance benefit to using Nixla when the underlying models are all kind of like the same, right? Like XGBoost and like the whatever regression models. And Darts has stuff for like using grid search to find the right features and things like that, and conformal. So I guess what's the comparative benefit, and what are you guys doing that's different?
That's a very good question. And actually, Darts uses a lot of the models that we have created. I think what we're doing differently in the whole Nixla project is try to build everything from the ground up. Not really, we don't identify as a library that is wrapping pre-existing models, but that is actually creating new models or new implementations of classical models that are very optimal. In this particular case, the ML forecast is an interface to pre-existing models of the SK family and LightGBM and XGBoost. But Stats Forecast, for example, it's a library where we took the classical implementations of Hitman from the R ecosystem and ported them to Python, rewrote them in a very efficient way, wrote our own optimization methods like the Nelder-Meet, and that's what makes it very, very fast. So it's a lot faster than PMD ARIMA, and actually most of the most used statistical methods of Dart, ETS, ARIMAs, exponential smoothings, thetas, are our own implementations. And on the other side, on the neural forecasting side of things, we're also publishing and researching new models. and proposing new models, and some of those models are included in darts. For example, the NBITS, which is a paper that we co-authored with Boris Oreshkin, or the NHITS. Those models are integrated in darts. So I guess the main difference that I would say is, on the one side, focusing on original, efficient implementations, and on the other side, what we think is particular or extremely different is that we natively built this to scale horizontally. If you try to scale with Prophet, with darts, with SK Time, with and all of those wonderful libraries, by the way, you're going to have a lot of problems scaling them. They don't natively support horizontal multi-cluster or multi-node scaling. So in my opinion, that's one important difference. But I don't know if you want to add something there.
No, thank you.
Can you pass the mic?
Thank you for that presentation. It was awesome. So you mentioned that for building the conformal predictor, you use cross-validation and then use that for determining the distribution of errors. Is that the way it works? Can you elaborate on it a little more?
Yes, sure. So basically that is the main idea, and in particular for time series forecasting, we don't want to estimate the distribution of all the errors, but we want to estimate the distribution of each step in the horizon. So for example, if we want to predict 12 steps ahead, we will be calculating the distribution of the first step and the second step and so on. So the technique is learning to quantify the uncertainty, not for the for the full horizon at once, but for each step in the horizon.
Got it. Thank you.
So because this method doesn't make an assumption on the shape of the distribution, you learn from data. Do you have requirements in terms of the data set size so that you can estimate that distribution accurately? What's the consequence on the size of the data set that's needed for accurate prediction?
Yeah, that's a really good question. I think the main idea behind conformal prediction is that you need to calculate errors. So if you have a lot of data, you can use that technique because you can information, right? So I would say that if you have more information, that would be best. Yeah.
And there is a specific number that's like minimum requirement, but that number it's going to be empirically determined by the specific data set that you have. So sadly, we don't have like an a priori general answer. But yes, obviously, if you have very few observations, you would like to use those observations as much as possible to train your model and not to evaluate the model. So it's this classical bias variance problem that you have and this classical data set size that you have. There was someone in the middle.
Thank you. The library looks really cool. I was just curious if you currently support or are planning to support like time series models from, say, TensorFlow, just as an example, or other kind of like, you know, iconic libraries that are used for time series besides sklearn.
Yeah, sure. That's an interesting question. We support neural forecasting methods in our library, Neural Forecast, and it is written in Torch. I think it is one of the main frameworks for deep learning, and we explored TensorFlow, but at the end of the day, we end up using PyTorch and PyTorch lining because it is really easy to use and it is really fast. Yeah.
And maybe that's also one difference between what we are doing and other paradigms. From the very beginning, we decided to split the paradigms. So if you are using statistical forecasting methods, then obviously you don't need the whole dependency hell that comes with more complicated frameworks. And that's why we decided to make it different libraries. Obviously, you can handle it with different methods, but that's why we decided to do it that way. But yes, in Neural Forecast, which is a PyTorch Lightning-based or PyTorch-based library, you can easily bring your own models as far as they satisfy the PyTorch paradigm and have a similar structure. And in our opinion, it's quite easy. If you're interested in bringing in models that come from other researchers, that's easy. That's, for example, Neural Forecast now supports not only our own research, but also research that has come out of Amazon or Google, like TFTs and other methods.
Thank you for. Thank you for the talk. I was curious whether or what you've done in the area of regarding to time series where the error distribution would change with time, because it seems like the conformal prediction sort of requires that distribution is constant.
Yeah, that's an interesting and important question, and I would say that I just explained before the main idea behind conformal prediction is that exactly you can estimate the distribution of the errors, but if there is a drift in the data and you could use that data to calculate the distribution of the errors, we should expect that drift will be captured by the technique. So the main I would say that you need to identify that drift of your data, and then you can use that technique on that drift of that change, and the technique will be capturing that change. Yeah. Would you like to?
Just we have been asked that question a lot, like how to handle a regime-changing time series data. And we're working on certain models that are better suited for those specific needs. Maybe some like early attempts that you can do, and we're about to publish that, is using the Arch and Garch family of models in the statistical library. And right now we don't support conformal prediction there, but one of our next releases is gonna include conformal prediction for all the statistical methods. So maybe for some specific regime-changing time series, the whole Arch family might provide a good baseline plus conformal prediction. But we're working on that. It's a very important topic. I think there is someone before.
I think we've probably got time for 2 more questions. Get this side of the room real quick.
Thank you. Thanks for the presentation. I closed my eyes. I pretended I was the Minister of Australia. I woke back up. But what was the outcome? How did the library perform? What was my decision logic? Can you guys conclude that, please? Thank you very much.
Thank you very, very much. So the outcome is that you were able to do wonderful forecasts for the different regions and also quantified the uncertainty, and you are probably running for office and becoming president of Australia after your wonderful job as Minister of Tourism. Thank you very much again. I think there was a question there. Yes. I think we can also handle the last question.
Quick question.
Yeah, sure.
Do we need to rename the columns like dates, DS, or something like that?
You don't need to rename them. If you, for example, instead of Y use I don't know, sales, you can define with our parameters what are you training on. So for example, if the target call instead of Y is sales, you can include the sales column, and exactly the same for all the other parameters. Yeah.
So the only thing that is required is that you have at least one ID, at least one timestamp, and at least one value that you want to forecast. But you can map it to whatever names you have.
Can I use ML forecast to do multivariate forecasting? Like, for instance, if I want to forecast energy consumption for the next 5 days, I can use historical data, but I also wanted to add the weather component to it. Can Can I use it in this case?
Absolutely. If the method supports it, you can use as many exogenous variables as you want, and all the methods that we showed support exogenous variables. So yeah, definitely you can include weather, you can include price, you can include like the index of certain commodities that might influence the consumption of energy, and that's definitely gonna give you some a boost in accuracy. We're also working on strictly speaking multivariate problems where you're trying also to measure the relationship between the different series and not only the relation between the covariates of a specific series. And you can find those like general multivariate methods in neural forecast. Someone else? I think we have time for two more questions. We tried to keep it brief so we get time to answer more questions.
Where was the question?
Yeah, thank you for the talk. I have a question regarding the distribution of the error. I think we just discussed. So is it better to remove outlier in that perspective? Like, what's your take on outlier?
Yeah, sure. In our experience, that improves a lot the width of the conformal intervals, and also you can, instead of removing the outliers, transform your data to make it more smooth. So, for example, you can use a Box-Cox transformation, and you can make the time series smooth. So, yeah, it is usually a good practice to take into account the outliers of the data. Yeah.
But what if like those outliers is somewhat meaningful? Because I always kind of get confused when it comes to forecasting. Like, is it actually like those outlier has like some meaning in the data? So like, how do we like handle those situations?
Yeah, that's interesting. One of the ideas that usually improves the forecast and takes into account the outliers is to include them, for example, as a exogenous variable. So, for example, if you know that in a specific day there was a huge amount of sales due to, I don't know, maybe because it is December or something else, you can include that dummy variable, and then you could tell to the model, here is an outlier, but I can explain why it is an outlier. So it will improve the forecasting accuracy and also the prediction intervals. Yeah.
Makes sense. Thank you.
We have some Nixla stickers for you if you want.
Can we give a big round of applause for Max and Fede?